Loud and sharing. Yeah, sorry. My computer refuses to share. Oh, now I think it's sharing. Is it? Can you see what's going on? Yeah, okay, perfect. So welcome once again. A few things about this. So what is this? This is kind of something between a reading group and an online seminar. And the reason why we started it is because we realized that we don't know who are the people that are interested in learning in games. For example, I was discussing some results with somebody from finance here at LSE, and she said, well, I have 2 papers that I read recently in the finance literature about learning and folk theorem. I didn't know that they care about that. So we understand that this is something that has many facets, many people from different places and from different kind of points of view are interested. So who we are trying to be a very diverse group. We have people from econ, computer science, finance, math, engineering. We have people from many different countries, many different universities, and this is who we are. What do we want? Well, clearly world peace, fame, and fortune. But other than that, we want to create a flexible framework, some kind of infrastructure that will enable people that come from different places to communicate about issues of learning in games or multi-agent learning or however you want to call it. To have a conversation that involves people from different disciplines, that involves young people, PhD students, and less young people, that is us, and where we can learn from each other and inspire each other. This is what we want. Also, we are well aware that people that come from different disciplines, they have different knowledge, different backgrounds. So, for example, the thing that I will present today, not probably, I know that there are people that are here that can present it better than me. It's a well-known result, fictitious play, but it is often that I find that people from other disciplines, they are less familiar with these things, and we're going to keep doing that and introduce, at least at some of the meetings, we're going to introduce some classic results as well as new contemporary research so that we can be inspired also by things that were done before. We're going to meet every 2 weeks during term time at least. And other than that, we are still kind of exploring where this is going and what is the appetite and what exactly do people need. So what can you do besides spreading the word and telling people that this thing exists and showing up? Please communicate with us. Please let us know if you have feedback. Maybe there are things that you want to do. Maybe there are things that you want to initiate. Maybe there are topics that you want to hear more about. Maybe you want to start, I don't know, PhD students group, discussion group, different reading group. Feel free. We are still kind of searching and learning what is the need of the community. The more you participate, the more you tell us what you want, the more we're going to be able to cater for your needs. So please don't hesitate to communicate with us and let us know what you want, what you need. If you have new ideas, if you want to present something, if you're thinking we're missing something, please welcome. This is for all of us as a community. This is more or less who we are and what we want, and we are quite flexible. Things will probably change with time when we realize what is comfortable for people, and the hour in which we meet is kind of compromised between hours that are comfortable for people in Europe and hours that are comfortable for people in Canada and the US. Okay, so that kind of concludes who we are and what we want. Now we're going to go into a very, very subjective and partial overview from my point of view about learning in games. Other people that will do an overview about that would probably present completely different things with completely different point of view from completely different angles. So please know that this is very partial, and they probably will in further weeks. But if I think about what learning in games mean for me, so I divide it into several categories that are sometimes interact, sometimes there is some intersection. First, we have the early game theory. So this is what we will present today. This is 1950s. They didn't even think about it as learning. For them, it wasn't learning. It was a method for solving a zero-sum game. Okay? Fictitious play was not introduced as learning. But this is the beginning of a conversation, of a mathematical conversation, of convergence of some processes that have some reason to something that makes sense. In some sense, converging to a Nash equilibrium. Exactly in what sense, that will be the end of the talk today. So this is the very early literature. Later, we begin to have really learning in games that is framed as learning. So we have Foster and Bora, Freudenberg, Levin, Hart, Mascolo, Germano, Lugosi, and more, and I'm probably missing a lot here in this very, very tiny list. And again, at the risk of grossly doing some gross injustice to the literature, I would say that in many senses, for me, it is more kind of a sophisticated searching mechanism. Very, very roughly, players play something, and if they are happy or not very regretful or framed otherwise, then they tend with high probability to keep playing that. And if they are not happy, very regretful, or something like that, then they generally search. And the question is, what is a proper algorithm under which they will end up in some sense converging to Nash equilibria, under which conditions, and so on. So this is one kind of very rough type of the literature. Simultaneously, we have evolutionary game theory. At the same time, we have evolutionary game theory, a very different inspiration to think about dynamics in games. So evolutionary game theory, naturally, even by the name, inspired by evolution. So we think of a society, we think of a population where either by imitation or by thinking that if you are successful, you have more offsprings, you gradually adopt more rewarding strategies. So the proportion of the population that chooses strategies that have higher rewards is using some rule to increase. Typically, it would be replicator dynamics, but there are other dynamics as well. If we compare the regret-based and evolutionary, at least for me, the main difference is that regret-based is a little bit of a bang-bang. I'm happy, I stay. I'm not happy, I randomize something very wild. The search is quite wild. In evolutionary game theory, we have kind of gradual change towards something that is sometimes a Nash equilibrium. Sometimes it isn't, sometimes it cycles, okay? But very different approaches to dynamics that follow some rule of trying to improve in games. And now we have a surge of interest in methods that are motivated by optimization, Q-learning, gradient-based learning. And these indeed are methods that were originally designed for optimization. So a single player that is, or decision maker that is making decisions in an environment that might be changing in some Bayesian manner, some stochastic manner, in some Markov way or not, and they're trying to optimize their choices. And these methods were working very well in many frameworks, so it became very tempting to try to apply them also to multi-agent scenarios. But as we all are very much well aware of, when you apply something that was designed for optimization to multi-agent scenarios, quite often it does not converge to a Nash equilibria, mainly because it's not designed to do so. Quite often you end up with the problem of trying to hit a moving target. While one player is trying to optimize, the opponent is optimizing as well. Both of them changing, several of them are changing their strategies simultaneously, and thus there is the risk of kind of cycling. And then you have lots of branches of the literature that begin with this disappointment of how come things that look perfectly reasonable end up not converging to Nash equilibria, or even not getting rid of dominated strategies sometimes, depending on the learning, and so on. And finally, the most recent part of this literature is probably when we begin to use deep learning and neural networks that, on the one hand, make the computations easier, faster in some sense. On the other hand, make the mathematical analysis much more challenging. It's really hard I mean, in this I'm no expert, but I know from experts that it's quite hard to apply mathematical analysis on deep learning. More or less, this is how I see. Again, with big caveat, this is very, very partial. Many topics are left out, but this is how I see learning in games or multi-agent learning. And I think that being familiar with the basic papers, the classic papers, can be quite inspiring when we're looking forward to applying them to more contemporary frameworks. Unless there are some questions. Okay, yeah, that's another thing. We are, at least I am not very formal in many ways. Please, 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 feel free. If I'm saying something that is not clear, ask questions. Stop and ask, please. And if there are no questions, then we move forward to go a little bit deeper into one specific paper. And I was, of course, well aware of fictitious play and what it means and some of the results, but to be perfectly honest, up until 2 years ago, I never properly read this paper. I knew it existed. I never sat down and read it. And when I did read it, an iterative method of solving a game, this is the title, I was quite happy with how elegant this paper is. It's short, it's kind of well-framed, you have 4 lemmas proving a very elegant result. Oh, there is something in the chat. Would we be discussing misspecified learning? If we want to, we will. Yeah, definitely. I mean, this meeting is mainly about fictitious play, but we are very happy to learn and to discuss any topic that you want to talk about. Okay, going back to an iterative method of solving a game. So this paper, it makes a really nice mathematical reading. It is written in the fashion or how math was written in the 50s. So very condensed, no examples, no discussions about, you know, how this paper is going to be applied in economics and make you very rich tomorrow. Just here is a problem, here is a theorem, here are 4 lemmas and very elegant proofs. Okay, so a few words. This serious looking lady is Julia Robinson, and she was a PhD student of Tarski. If you check her Wikipedia page, you'll see how magnificent she was. In the late 40s, she spent a year at the Rand Corporation in Santa Monica, and then she did a lot of mathematical game theory. And this is when she became familiar with this problem of what we call now fictitious play. So what's the problem? What is this thing about? So she's looking at a zero-sum game, finite number of actions for each player, 2 players, finite number of actions, a zero-sum game, a very traditional one. Player 1 is choosing the rows, he is the maximizer. Player 2 choosing the columns, the minimizer, and so on. So each player at each period plays a pure best reply to the empirical distribution of actions of the opponent up to that period. So, okay, this requires a little bit of unpacking. And we'll do it formally in a minute, but less formally. At each period, player 1 looks at the past distribution of actions of player 2. Suppose that player 2 played 1/3 of the period, his first column, and 2/3 the second column. Now player 1 checks his actions, that are the rows, finds one row that gives him the best, the highest. Player 1 is the maximizer, they want the highest payoff against this distribution of player 2. And this is the action that player 1 chooses to play in the next period. A similar thing is conducted simultaneously by player 2. So player 2 is checking past distribution of rows of player 1, okay? And he selects an action, a column, that minimizes the expected payoff, the expected reward, if this past distribution is indeed the action that is going to be played by the opponent. So best reply to past empirical distribution of the opponents. This is the method, this is the mechanism of learning of fictitious play. And the question that was posed by George Brown as a prize problem at the Rand Corporation is, what can we say about the limit of this process? Yeah, there is some logic to that. I'm best responding to the history that I observed. Does it give us anything? Does it lead to anything? This is the problem that Robinson was set to answer, and answer she did. So we need some notations. This is a classic zero-sum game. We have two players. Player 1 is the maximizer and player 2 is the minimizer. And we have a payoff matrix Aij. When I represents the rows, suppose we have m of those. M the columns, suppose we have n of those. Everything again is finite. And she is looking for solving the game. So in zero-sum game, you can say that you can solve the game because zero-sum games, we know, finite, they have a value and they have optimal strategies. And when we're looking for solving the game, we're looking for an equilibrium for this game. And in zero-sum game, we know that an equilibrium is any combination of optimal strategies, optimal strategy for the first player and an optimal strategy for the second player. And these equilibria give us always the same thing. If there are many equilibria, they always give us the same thing. They always give us the value. So this is kind of a well-known thing. If X and Y are the solution, meaning X is an optimal strategy of player 1, Y optimal strategy for player 2, then the expected reward, we sum over the rows, we sum over the column, probability of choosing the row times probability of choosing the column times the reward of the column. This is equal to the value of the game, and no player has a profitable deviation, meaning if the column player, this is player 2, is trying to maximize, I'm guessing you can see my cursor, he's trying to minimize, so he's looking, sorry, player 2 is trying to minimize, he's looking over all his column, and for each column, he computes what is the expected reward given the distribution over the rows played by player 1, then this value is indeed the minimum that this player can achieve. And similarly, for our row player, this is the maximum that they can do given the strategy profile Yj of player 2 that is optimal.
Do you mind if I ask a question?
Please do.
So yeah, I just wondered, on the previous slide, so the plays are stochastic, is that right? Like each player is choosing over a distribution of possible moves, or they're choosing over discrete moves?
Okay, you're asking whether the players are allowed to choose mixed strategies?
I think that's what I'm asking. I'm not really an econ expert, so, but yeah,
Okay.
I'm seeing like the domain of this variable. I'm wondering if it's a random variable. Is this kind of equality hold in expectation? Does it hold for like, because it seems like to me the best response would be you have your distribution and then you choose the highest probability from that rather than like sampling over it.
Okay, I will try to answer and then you tell me whether have I answered. So I will try to answer. So in a zero-sum game, often wise, the optimal strategy is a mixed one. So the choice of an optimal strategy, if you want to find something that is indeed optimal in the grand sense, it has to be from the simplex. So to solve the game is to introduce a strategy that is mixed and that is optimal, meaning it is the best response to the opponent, and regardless of what the opponent is doing in this case, you cannot do better than that in some sense. No, that's not true. It is the best response to the opponent, and both pairs are best responding to the opponent. So this solution, when I say X and Y here, these are mixed strategies. However, the method of learning, the algorithm that I just described, involves each player at each period choosing one row or one column, choosing to play a pure action. Okay, so and the rule according to which that pure action is chosen, player one is looking at the distribution of player two's pure actions, computes the empirical distribution. So 1/5 of the time that one was played, and 2/5 the other one, and so on and so forth. If you compute the empirical distribution, it's as if you imagine a mixed strategy for player two. This was played some of the time, some fraction of the time, and that was played another fraction of the time, and so on. And then you choose one pure action, one pure role for player one that is the best response to that historical empirical distribution. So I see maybe why it is a bit confusing, because when we say solution, we mean a mixed strategy. But in the algorithm that I just described in the fictitious play, they are actually choosing pure strategy.
Okay, great. Yeah, that's a great answer. And you did answer my question. I guess just like my intuition is still a bit bothered by that. I'll just pose one question, and then I don't know if it's possible to answer it. If not, we can leave that as open. But if I'm player X and I'm playing against player Y, like some part of my, if we're talking about learning in games, something is going to be about learning the distribution over Y, like Y's actions. But then the equilibrium says, I want to minimize my cost under an assumption that the opponent is playing randomly according to their distribution. But that seems a little, but it seems like their optimal, I don't know, I'm just wondering if the opponent plays according to like, yes.
Can I try and guess? I'm not sure, I'm guessing. Are you wondering whether it is wise to play like that?
Yes, essentially.
And the answer is not necessarily at all. Okay. So, and we will discuss that at the end. I mean, if you're wondering whether, so for example, if I know that my opponent is using this method, is it wise for me to use it as well? Absolutely not.
Right. I mean, you'll reach the equilibrium, but you might be able to exploit the fact that they are choosing some like suboptimal actions some percent of the time. So, okay, great.
I mean, even saying you will reach an equilibrium is not a very clear thing. In some sense, and then that will be the end discussion of this, but in some sense, things go to an equilibrium, but only in a very limited way. And we'll talk about that, definitely. Good question.
Okay, thanks.
Thank you for asking. Okay, so if you look at the paper itself, how she describes it in a slightly different way. She calls it a vector system. So A is the payoff matrix, and she describes what she calls a vector system for A. Now, keep in mind what we just said, that at each period, each player chooses kind of the best reply to historical distribution. These are the notations of the paper, and we'll interpret that based on what we just understood about what is fictitious play. So actually in the paper, she begins with some arbitrary vector U0, some arbitrary row, and some V0. I skipped that. I don't think it's helping the understanding, but if you go there, know that it's there. Think of the game again being played repeatedly. At the first period, player one chooses some row U1, and player two chooses some column V1. For the first one, we don't need a specific rule. Now comes the second period. And again, player one chooses a row and player two chooses a column. In the vector system, we have the addition, the sum of these rows here, and the sum of these columns here. So U2 here is a sum of two rows. It's a vector that is a sum of two vectors, a sum of two rows, and V2 is a sum of two columns. And here it should be 3 and not 2, sorry for the typo, U3 and V3, and so on. What is the rule according to which we decide which row to add to the sum in this period and which column to add to the sum to this period? It's a similar rule as we discussed in the previous slide. So player one is looking at VT, okay, at V, say V of 1, okay? And they're looking at the column that was chosen by player two in the first period. And they are choosing the row that corresponds to the highest entry of that column. I want to maximize, given that this is the action chosen by my opponent. So VIT, the row AI here, the row AI of the matrix of the payoffs A, that is added to the sum of the rows of player one, is the row that corresponds to the highest entry of the sum of the opponents. Now, of course, if it's the highest entry of the sum, it's also the highest entry of the average, and therefore it's the highest expected payoff if you think of this as a distribution, okay? And so it's as if player one is choosing the best response to the empirical past distribution of actions of player two, and playing that action. And when I say playing that action, I mean you add that to the sum. Similar thing is done by player two. Player two is looking at the vector that is the accumulated sum of the rows that were chosen by player one. And player one is asking itself which entry, which column, which entry of this vector, or this row vector, which entry within that vector gives me the minimum. And this is the action chosen by player two to be played in the next period. So this is fictitious play. Okay, this is what we're describing here. What she calls a vector system is what later we call fictitious play. Are there any questions about this procedure? If not, let's do a very small simulation. So this is the familiar and loved rock, paper, scissors. And this here on the bottom left corner, I'm reminding you of the rules. Suppose that player one in the first period chooses the column 0, -1, 1, and player two chooses the column 1, -1, 0. So the third column is chosen by player one, and the first row is chosen by player two, and the first row is chosen by player one. Okay, what do we do now? Player one is checking out the vector of player two. He's looking for the entry that gives him the highest payoff. This is the first one. This is the first entry. And therefore, for the next time, for the second period, the action that is going to be played by the first player is again the first row. So U2 is now the sum of, well, besides being a rock band, is the sum of the first action, the first vector, plus the second one. Okay, are they essentially doing a minimal type of optimization? They are doing some type of optimization. They are optimizing, this is a question from the chat, they are optimizing against past actions, against past distribution of actions. And are they, well, yes, that's exactly the question. Do we end up with some kind of min-max? Good question. Yeah, in some sense, the answer is yes. And I'm sorry that I keep apologizing in some sense, because it's a little bit more subtle than saying, yes, absolutely, they get min-max. They get optimal strategies in some sense. Okay, so this is how player one was deciding on what they're going to play next. Now player two, he's thinking what to choose in the second period, and they're looking at the first row of player one. They still don't know the second one. So they're looking at the first row. The first row, the minimum entry was the second one. So player two is going to choose to play the second column. Okay, so player two is choosing to play the second column, and to that column we add what is optimal against past behavior, and we get V2. Let's do it one more iteration so that we're perfectly clear. Now, this is the accumulated of player 1. Was it? Yes. And the accumulation of player 2. Now, player 1 is looking at player 2. This is the sum of the two columns that were played by player 2. And player 1 is looking for the optimal, the maximal entry. And this is the last one. And therefore, player 1 is going to choose to play the last row. And this is going to be added to become U3. Similarly played player 2. He's looking at what player 1 was playing so far, and he's looking for what's the best response to that, what gives him, what column will give him the lowest payoff, and that's going to be the second one. So player 2 is going to play the second column, and this is going to become V3. This is the process. Again, we didn't say anything about where it's going. We just described and demonstrated and simulated the process. If there are any questions about the process, now is an excellent time to ask them.
Could I ask, U1 and V1 in this example, were they just initialized arbitrarily?
You can initialize them. Okay, actually, she initializes them even more arbitrarily when she adds some random U0 and the V0 that can be any vector as long as it's finite and from this dimension. We just begin completely arbitrarily. Are you thinking whether it does better if you choose more cleverly the beginning?
Yeah, I mean, I would think it would, but I was just in this example, I think it seems like we glossed over how we chose initially. So I was wondering if it was just kind of arbitrary.
No, it's even more wilder in the in the original script. He also added U0 and V0 that come from nowhere and can assume any values. So no, the beginning, because the question is what is the limit, basically, in the long run. So the initial point, it wouldn't send us to too many different directions. But a good question, Steve. Thank you for the question. Are there any more questions?
Yeah, Galit?
Yeah.
I guess it's something similar, but does the tie-breaking rule play any role in the result?
Good question. Yeah, good question, because I didn't specify. There can be several. I mean, in the example carefully chosen so that there are no ties, but at least in the beginning. But there can be ties. No, you can choose any action that is a best response, and the mechanism would still work. Definitely.
And it might not even be consistent, I guess.
Yes.
Okay.
Exactly. You can decide that, I don't know, in odd periods, you choose the best response with the smallest index, and in the even periods, another one. And then at the beginning, you feel sick of your rule and you want to entertain a different rule. It would still work. Yeah, good question.
Thanks.
And there is also a question in the chat. There will soon be a tie. Yes. So in a tie, you can choose any best response. Yes. Excellent questions, people. I have to admit, it's the first time that I'm formally explaining and presenting this result, and it's nice. I enjoy it. It's an elegant one. Okay, so what's the theorem? I mean, I keep saying, yeah, in some sense, what sense, what is it that we get? What is the, yes, we're best responding to past, what do we get? What does it give us? So what does it give us? We look at the accumulated vector of choices. So this is a sum, U of t is a sum of all the rows that were chosen by the first player along this process. So a very, very large sum. And we divide it by t. So you can think of this as the average reward, okay? The average reward, it's a vector, okay? So it's the sum of all the choices of the first players, of all the payoffs, all the rewards of all the choices of the first players, and we divide it by t. So it's average reward for the choices of their t. And we're looking at the minimal entry. So suppose that player 2 is best responding for that, and they are choosing the column that will minimize this average. The limit of that is the same as the corresponding limit for player 2, meaning now we look at the sum of all these columns chosen in the first period, in the second period. This is V of t, capital V of t. It's the sum of all these choices. And we divide it by t, so we get the average. And now suppose that player one is best responding. Player one is considering this vector of this column vector, and they are looking for the highest entry. Suppose that player one is best responding for that. What can player one do? Well, none of them can do any better than the value. The limit of this thing is the value. What does it, okay, before we move forward, what does it mean? It means that if we look at the distribution of player one, this distribution is an optimal strategy. If you play this distribution at every period, then it is an optimal strategy. So we compute, if we wish, an optimal strategy in this way. À la limite, it gets to be as if the marginal distribution is an optimal one in some sense. Okay, player one cannot do any better than that. Similarly, player two, we end up at a limit that is an optimal distribution for player two. Okay, so we consider the empirical distributions of actions for player one along all this process. And this is a distribution according to which an action is chosen in the expectation. Best responder player one will give him the value, player two will give him the value. Similarly for player two. In expectation, best response of player one will give the value. So what she proved is that we solve the game. We compute an optimal strategy of player one, and there can be many, but we compute one. We compute an optimal strategy of player two, and we compute the value of the game. And therefore, this solves the game in some sense. The proof. The actual proof, and I promise will be done within an hour, so we might skip a few things, but I still want to go into at least some of the things. The proof is by 4 lemmas. Three of them, the first 3, they are simple, easy to show, and very nice. The 4th one is where the mathematical machinery gets a little bit more involved, and we will say a few things about that, but even that, I mean, a clever undergrad can very easily take this paper and completely understand what's going on there. So if you need a topic, an interesting topic for a dissertation to give students, then this is highly recommended. So here is the first lemma. The first lemma says that if UV is a vector system for A, so to remind you, what do we mean? When we say vector system, we mean U is this sum of all the rows, and V is this sum of all the columns. Then, if we look at this creature here, the maximum over all the entries of the columns, V's are the columns, minus the minimum over all the V's of the rows, this is non-negative, the limit. So all along the way, the limit is non-negative. Okay, so I'll give you a little bit of the proof. Okay. So suppose that Y and X are the empirical distributions. Okay, so Y is a vector of probabilities. It is within the simplex, and this is the proportion, past proportion with which player 2 chooses his pure actions, and similarly X for player 1. Okay, what is the first expression that we have here? Max I V I T. What is that? What is that? It is T times, okay, the maximal over all the entries, over all the actions of player 1, over all the rows, okay, the maximum over the expectancy of the payoff, given that Yj is the empirical distribution of player 2. So now, think about player 1 best responding to the strategy Y by player 2. We know that if player 1 is maximizing, if player 1 is best responding to a strategy, they can guarantee at least the value. Therefore, this expression here, max I sigma j it is at least V, at least the value of the game, and the T remains a T. And so this is from the ability to best respond to any given strategy of the opponent and guarantee to get at least the value for player one. A similar argument holds for player two. So player two is looking at the rows that were chosen by player one, and they are looking for the minimal entry. But again, we can think of Xi as some distribution played by player one, and we can ask ourselves, what is the best response of player two? So player two is looking at these rows, he's looking for the entry that gives him the minimal reward. He's best responding to that. And we know that if player two is best responding, zero-sum game, to any given strategy of player one, he can guarantee never to pay more than the value. He can guarantee that he gets less or equal to the value. So we have two inequalities here, and it's easy to see that if you combine them, you get exactly what is written here. Again, with a little bit of hand waving from my side, but more or less, this is the idea. This is the proof of the first lemma, first out of four. If you have questions about the proof of the first lemma, please ask them. Okay, so this maybe it's quite intuitive for people with a game theory background. Now, for the statement of lemma 2 and actually lemma 3 and so on, we need a definition that actually gives maybe even a better answer to the question of Ilan. What is an eligible row or column? So, definition. And that's, I think it's the last definition we need. If UV is a vector system for A, so if U and V are the accumulation of rows and columns according to fictitious play, then we say that the ith row is eligible in some interval of times of periods, T prime. It is eligible if, provided, there exists some T1 that is somewhere between T and T prime, and such that VI of T1 is the maximum that player one can do, the best that player one can do against the strategy of player two. In other words, the row I is eligible for some period interval if it could have been chosen by player one at some point as a best response somewhere between period T and period T prime. It is eligible if it could have been chosen, if it was a maximizer. Doesn't mean that it was actually chosen, but if it could have been chosen, then we call it eligible. A similar definition holds for the second player. So the column is eligible in some time frame between T and T prime, provided that there exists some T2 such that player 2, when minimizing somewhere between period T and period T prime, could have chosen this column as its minimum. Okay, so think of eligible rows and eligible columns as rows and columns that could have been chosen according to the algorithms of fictitious play. They were best responses at some point between these time frames for the historical distribution of the opponent. This is eligible. This is the second definition. And here is the second lemma. And I think it gets a little bit less intuitive and interesting here. I mean, this is where things are begin to be not trivial. But again, if you would think about it, you see why it holds. Given a vector system UV for A, if all rows and columns are eligible in some interval, then we're looking at the row U of S plus T after this interval S plus T. We're looking at the highest entry and the lowest entry of that row, okay? And they cannot be too far away from each other. Similarly, from the columns, the A stands for the maximal number that is written, absolute value of the numbers that are written in the matrix. Now, we're going to give the proof in a minute, but why is that? If all rows were eligible, then each one of them at some point was the maximum. They cannot be too far apart. Okay, these entries cannot be too far apart. Okay, there is a bound to how far apart they can be if they were both optimal at some point. And similarly for columns. Okay, and this is exactly where the proof will take us. So this is the statement to remind us so that we don't forget the statement. And now, how does the proof go? So I remind you that all rows and all columns, we assume now that all rows and columns were eligible. So let's take a look at the uj of s of t, that is the maximum, okay, at the point of s of t. So we look at the maximum at the end of this period, at time s plus t, when at the end of this thing, when we look at it, what is the maximal entry? There is some j that is a maximal entry, maybe more than one, but there is one, okay? And this j is eligible, this column is eligible because all columns are eligible. So specifically, at some point, it was the minimum, it was chosen as the minimum, okay? And then we know that if t periods passed since then the maximum that we can add from the time that it was a minimum up until the end cannot be more than a times t. Each period you can add at most t. So uj of s plus t is smaller or equal than the minimum, and therefore, and basically this is all the proof. Because look, what we have here is that uj of s plus t, which was chosen to be the maximal entry. So this is uj of s plus t, is smaller or equal than the minimum plus at. Okay, and the minimum as well, cannot be more than minus at away from the time that itself was eligible. Okay, so if two columns were eligible, they cannot be more than 2at far apart, because this is the most that you can accumulate, the most difference you can accumulate. Okay, this is the proof of the second. And lemma 3 is already beginning to bound what we really want. The maximum over the columns and the minimum over the rows. This is getting very close to what we want to prove, okay? And this bound, you can see that this bound does not depend on S at all. So take S to be very large, and you can see how it means that somehow if you take the average, they converge to each other. However, we are still under the assumption that all rows and columns of A are eligible, which has no reason to be true in general. Okay, so we will need another thing to tie up things, and I want to finish this part of the presentation. So I'll skip the proof and I'll tell you that it's not difficult, the lemma 3. And then I'll move to lemma 4 that ties things up, just to tell you, and first to encourage you to take a look at the paper, because really it's not too difficult, but also to give you some clues as to what is needed for the fourth lemma. So far we managed to bound differences between rows, columns, maximum, minimum very well, but we kept having the assumption that all rows and all columns are eligible. So the question is, how do you tie things up and show how things are working? The fourth lemma basically tells us, as you can see, divide both things by t and we get what we really want. This basically sums up the proof of the theorem. And I will give you a proof outline so that when you read it, you know what to keep in mind. If all rows and columns are eligible, then the previous lemma we just saw, it applies and it just gives you what you need. It gives you the epsilon difference between them as time goes by. And here comes the thing that is very new for lemma 4. Else, you have row or column, or maybe both, that were kind of never from a certain time on that are not eligible. Therefore, we can remove them, we can ignore them, and the proof of lemma 4 is by induction on the matrix size, okay? So if everything is eligible, we can apply the previous lemma. If something was not eligible, we can delete, we can ignore, we can disregard a row or a column, reduce the matrix size, and apply some kind of an induction on the dimensions of the matrix. Clearly, the statement holds for one-on-one matrix when they have only one choice of things. So again, this is less a very deep dive into the understanding of the proof and more an encouragement to take a look at the proof and at this not very nice paper yourself. Later, more works showed that similar things happen for games that are solvable by iterative elimination of strictly dominated strategies. This is from the 90s. For potential games by Mondre and Shapley, 96, there are 2 papers about that. For the game that has generic payoffs, not going to go into what is that, and is in the format of 2 on N, this is 2005, so later. So there were more recent works looking into fictitious play. However, we have from Shapley a variation of rock, paper, scissors, where things might cycle, so some kind of different type of convergence, which maybe brings us to the discussion that I was hoping to have about what does it mean to converge. So what is it really that we proved here? What type of convergence to what do we have here? So we have that if we consider the empirical distribution of rows of player 1, actions of player 1, along this infinite history, at the limit, this gives us an optimal strategy for player 1. And if player 2 is best responding to this distribution, to this empirical distribution, they cannot get more than the value. Similarly, we get that if player 2, we look at his past choice of actions and we'll take the average, what you get is something that approaches more and more towards an optimal strategy of player 2. And of course, if these are actually played, optimal strategy of player 1 facing an optimal strategy of player 2, we will get the value of the game. But as you asked, very rightfully so, what does it say about the payoffs? So if we go back to the rock, paper, scissors, suppose that we end up somehow playing 1/3 of the game this cell, 1/3 of the game that cell, and 1/3 of the game that cell. If you look at the empirical distribution of rows, yes, it's 1/3, 1/3, 1/3. This is an optimal strategy. If you look at the empirical distribution of the columns, 1/3, 1/3, 1/3, also an optimal strategy. But clearly the payoff is very, very far from optimal to player 2. He is getting the worst here. He is getting 1 and 1 and 1. Because while the marginals, the average of the marginals converge to something optimal, we said absolutely nothing about the limit of the convergence of the joint actions. And they really don't have to be something that is close to optimal and close to the value, okay? It may cycle in a way where things are stayed away from optimal. The value can be bounded away from what we get in when the players actually play this fictitious play. So this fictitious play is a method of computing things. And as a method of learning, if you really want to think of it as learning, at some point you have to stop the learning and start applying what you just learned, okay? And start using that strategy. So we get a very weak type of convergence. We get the convergence of the marginals. We don't get convergence of the joint distribution. And of course, okay, we don't get the strongest convergence, which is last iteration convergence. So if we want to think of learning at games as a procedure where we adjust, where the players adjust their strategies, trying to improve their strategies simultaneously, so as the game proceeds, as the algorithm moves on, as the thing unfolds, the players get closer and closer to playing in equilibrium, to playing optimally. Then we don't get that here because they just choose pure strategies each time. They don't get closer and closer to playing optimally. So I hope this gives a more accurate answer and also maybe gives room to think about when we talk about converging to a Nash equilibrium. What do we mean? Here we have a very weak sense of convergence. It's just the marginals. It's not the joint. It's not the payoffs. There is a stronger sense. We want the joint to converge to the payoff of a Nash equilibrium, to the value of the game, which exists in a zero-sum game. And then we want last iteration convergence, which is even stronger. And this is exactly in time to stop my presentation and to stop sharing and to ask you guys, oh my God, the sun is really in my face. Sun in London, okay. And to ask you guys if you have any questions, anything you want to say, ask, share. Yeah, please unmute yourself. Feel free. This discussion now is completely free. Feel free to say whatever you want.
I did have a question. I guess you prefaced the paper by mentioning it's written in the style of like 1950s math and economics, which is really abstract. Could you provide any sort of like working example of what the players represent and what their moves represent and what the result kind of implies in a kind of a toy example?
Okay, I can look up whether there is something like that, but basically this specific paper, what they have in mind is a finite zero-sum game. So in econ, what would be a finite zero-sum game? You would need something where the interests of the players are really against each other, a war or something like that. Easier to think of it as toy examples like rock, paper, scissors, matching pennies, because then it's
that's fine. But could you say more about what's the rock, paper, scissors analogy here? Like, how does that map to the formalism?
Sure. Okay, so I'll go back to sharing. Oh, of course, yes, I understand your question. So this is the rock. This is rock, paper, scissors. So we know that if you suppose that the first column is rock and the first row is rock. Okay, so if you play rock against rock, you get a 0, right? Nobody's winning. This is a tie. And what is best respond to rock is paper. So the third column will need to be paper, and then the second column will need to be scissors. So there are combinations where player 1 wins, and this will give 1. So rock, this is scissors. So when player 1 wins, he gets 1. When player 2 wins, it's a -1. And if it's a tie, and in rock, paper, scissors, a tie is when both players are choosing the same action, rock against rock, paper versus paper, and scissors against scissors, then you get a 0. So this is the analogy. You have 3 actions, 3 pure actions. For each pair that is not the same action, each pair of different actions, you have a rule to determine which one is better, and it's kind of circular. Rock breaks scissors, scissors tear paper, and paper wraps the rock. So this is the analogy. And the reason why it is used as an example in many evolutionary game theory and learning dynamics is because it's a problematic game. It creates many cases where dynamics of learning tend to cycle rather than converge to an equilibrium. This is, again, not the scope of this specific paper and presentation, but if you check out evolutionary game theory in rock, paper, scissors, you will find that it's a prominent example of how to get things to go completely wrong. And if we
in this paper, what's the result telling us? That there's a strategy that players can play which will converge to kind of a fixed point of the game, but that might not be, I mean, I guess the fixed point would be one player is constantly winning and the other player is constantly losing.
The equilibrium in rock, paper, scissors. Okay, if you played rock, paper, scissors as a child, then you probably know that the best that you can do is to be unpredictable, to randomize. And because if your opponent knows what you're going to play, they know how to beat you. So the best that you can do in mathematical language would be to maximize entropy. You want to choose 1/3, 1/3, 1/3. That's the best that you can do.
And that's the result. I mean, the result is suggesting that that's the equilibrium according to this type of like UT+1. You take a certain action, VT. Okay.
So the fact that it's an equilibrium can be computed using more simpler things. Well, the result that we just showed is telling us that if the players are using this fictitious play mechanism, if you check out the distribution of the rows chosen by player 1, you will see that it converges to 1/3, 1/3, 1/3. You will see that with time, approximately 1/3 of the time, he chose the first row, 1/3 of the times it chose the second, and 1/3 it chose the third. And similarly for the column player, for them as well, the best strategy, the optimal strategy in this specific game is 1/3, 1/3, 1/3, and it says that again, for them as well, it's going to converge towards 1/3, 1/3, 1/3. This is what it's telling us.
Okay, thanks.
Sure. Are there more questions? Okay, so I'm going to stop the recording.